So we are studying about perfect graph, and then we want to prove this perfect graph theorem. It's a contextual by Birch and then proved by robust, so it's now perfect graph theorem. Means, which said that if she is perfect, then if and only if she complement is perfect. And then how did robust prove? To see this, we know that we know that this holds, right? Whenever you have a chromatic number and you multiply with its independence number, then it's at least 10. Because this means that you can partition the vertex set into how many independent set, and each one of them has size and most alpha of G, because alpha of G is the size of the largest independent set. So the number of vertices here is n, so you have this inequality. But for perfect graph, we know that this is same as omega. So omega of G and alpha of G is at least 10 for perfect graph. But here, if you take the complement, it's same as alpha of G complement and then omega of G complement. So it has same value, which again at least 10. So from this, you have the idea that if converse also holds, then you can prove a perfect graph theorem. So what robust prove with this complement, if this holds for all induced subgraph H of G, then G is perfect. If we know this, then okay. So, and the other direction is also trivial by the logic that I just explained. Then this trivially implies the perfect graph theorem, because this condition holds for G, then this naturally holds for its complement. As I mentioned, you take the complement in each H, then it's the same value, this expression. So we will prove this, but we use the shorter proof, which was found by Kasparian. And in order to discuss this, let's define a terminology to make the discussion more convenient. We say that a graph is P-critical or minimally imperfect if a graph G is P-critical if G is not perfect, but any proper induced subgraph is perfect. Then we say that this is P-critical. Okay, now let's prove this lemma about this P-critical graph. If S is a table set, which is same as independent set, in a P-critical graph, G, then the Kling number in G is same with Kling number after deleting this independent set. So deleting an independent set does not decrease the Kling number in P-critical graph. So let's prove this. Since this G is P critical, we have that its chromatic number is bigger than its Killing number. And for its induced subgraph, proper induced subgraph, G minus S, its equality. And what do you do? Once you have this proper coloring of G minus S, you just take a new color and then you color all the vertices in S with this new color. So we have what? This is at most the chromatic number of G. Okay? And this is strictly bigger than omega of G because this is P critical. And this is actually at most this Killing number of G minus S. And then that's same as this. So what do we have? So this and this has only gap 1. But this is strict equality. And what do we have? This and this has different 1, and that's strict inequality. Then everything else has to be equality. This is equality, this is equality, this is equality. So we have this conclusion. So now we can prove what we want. A graph G is perfect if and only if its Killing number of H times intrinsic number of H is at least the number of vertices in H for, wait, sorry, so here it has to be the number of vertices in H, not L, which is the number of vertices in G. This is for every induced subgraph H of G. So we prove this. And we only have to show this direction because the other direction is easy, as I mentioned. But since every not perfect graph, the imperfect graph, has a P critical induced subgraph, it's sufficient to show that this is smaller than N when this G is P critical. Graph of ordinal. So if we prove this, it's sufficient. Because if some graph is not perfect, then then you must have a smallest not perfect graph. And that subgraph is P critical in the subgraph of the graph. And it's so we can just take that graph and then let's assume that that's your G. And then for that, if this equality holds, and that means that if this holds for all H, that means G does not contain P critical subgraph, P critical induced subgraph. That means G is perfect. So if we show this, then this implication holds. So let alpha be alpha of G and omega be omega of G. So we take a maximum stable set. So maximum independent set, which has size U3 alpha S0 in G. And let's say this S0 consists of the vertices x1 to x alpha. And what do we know? We know that here, once we delete an independent set, the clique number decrease, and also chromatic number, so if you move it, this is one less. So anyway, so this omega is still same, and then the clique number, chromatic number reduces by 1. So we know that each G minus Xi, so if you delete it, is omega 12, meaning that it can be partitioned into stable sets, the independent set, and let S R minus 1 omega plus 1 to S R omega. Let's say this is R. This to be the independent set in an optimal coloring of this G minus XR. Okay, so you delete one vertex in G, then everything else partition into this independent set. Then also, okay, so roughly our plan is you take many independent sets and many clique, and then see how they are intersecting. And then we will show that those intersecting pattern is not possible to derive a contradiction. So these are the independent sets. And for each, say, J between 0 and alpha W, the previous lemma, we apply previous lemma to here's that the clique number of G minus Sj is omega. So you want to find the clique Qj, which is disjoint from this Sj. So maximum clique Qj in this G minus Sj is W clique, omega clique, sorry. Clique of size omega in G that avoids Sj. So what we want to claim? We want to claim that the Sj, Si intersection with Qj is not empty for I different from J. So whenever I and J are different, they are intersecting. Right? But by our choice, they are not intersecting if I and J are same. So this will give us an intersection pattern. And then later we will show that that's impossible. What do we know? The sets SR minus 1 omega plus 1 to SRW, these partitions the vertices of G minus XR into omega independent set. And this Qj contains at most one vertex from each. So there are omega of them, and then Qj cannot contain 2 from 1. So it contains at most 1 from each. Because this is clique and this is independent set. So if this XR, which is deleted, is not in Qj, then this has size omega and there are omega sets. So it must contain exactly 1 vertex. Okay. If this XR is in Qj, then what happens? Then this Qj has only omega minus 1 vertices other than XR, and hence this is exactly one of the sets. And highlighting this one of G minus XR. Okay, but what do we know? S0 itself is an independent set. So the Qj must contain at most 1 of them. So yes, this Qj can only have 1 vertex in this S0. There is what? So you have x1, x2, xr. And for this, so you consider the coloring. So this gives you this set of, this is coloring of G minus x1 and G minus x2, dot, dot, dot. And so on. And this Qj may contain only 1 of them. And for the rest of them, this contains 1 element from every one of them. But for this particular one, that this contains this XR, so this is X alpha XR, it contains 1 from every one except exactly 1. So what does it mean? It means out of all lists here, this is missing exactly 1. I mean, this is missing elements from exactly 1 independent set, and it contains 1 from every other. There is at most 1 independent set in the entire list of S0 to F alpha omega. So I mean, if this listed everything here from S0, then everything is 1, 1, 1 here. I mean, it intersects with everything at 1 vertex. That is missed by Qj. On the other hand, what do we know? We know that the Qj intersection with Sj is 0. It's empty set. As Qj was chosen to be a maximum clique in G minus Sj. So we identify where it misses. So everything else, it's so Qj intersection with Si is 1 for all I which is not J. So this is hold. This hold. If this is given, say 1, we know. So now what? Now you consider, now you are very close to what we want. So we want to show that this intersection pattern is impossible. Why? Let A be the incidence matrix, which is n by alpha omega plus 1. So that you write down or S0, S1, S alpha 0. And then here you write down all the vertices you want to be n. And you write down 0 or 1. If this one belongs to S0, then 1. If the next one does not belong to S0, it's 0, and so on. So this is the incidence matrix. And B is again n by alpha omega plus 1 incidence matrix of Q0 to Q alpha omega. So what? Again, the same vertex ordering, Q0, Q alpha omega. And then what do? You consider A transpose B. Then what does it get? You have S0 to S alpha omega, Q0 to Q alpha omega. And then what's this entry? This entry is nothing but this multiply with this. So compound-wise multiply, and you add. But what does it count? It actually counts the size of intersection. So you get the matrix, which is 0, 0, 0 on the diagonal, and everything else is 1, which is J minus I, where the J is all one matrix, and I is the identity matrix. Yeah. Okay, but what do you know? Since this J minus I is non-singular, both A and B must have length at least alpha omega plus 1. So this is alpha omega plus 1 by alpha omega 1 plus 1 matrix, right? So it has to be at least that. But what do you know? This is n by alpha omega plus 1 matrix. It's n by alpha omega plus 1 matrix. So n has to be at least alpha omega plus 1 to make sure that A and B have a length at least alpha omega plus 1. So this shows that omega of G, alpha of G, is smaller than n, which proves what we want. So if it is minimally imperfect, then this holds. That means if this is imperfect, there must be an induced subgraph satisfying this equality. You take the contrapositive, then this implies that it is perfect. Okay, so this was a nice application of this linear algebra to prove a graph theoretic statement. And also, maybe I mentioned one more thing before concluding this section. When there's conjecture this perfect graph theorem, he also conjecture strong perfect graph conjecture, which is now theorem, which completely characterize the complete graph. I mean, perfect graph. So, what's the conjecture? The odd cycles and their complements are the only p-critical graph, the minimally imperfect graph. So in other words, a graph G is perfect if and only if it has no odd hole or complements of odd hole. Again, I mean, this is stronger than perfect graph theorem. This implies perfect graph theorem. And not only that, this completely characterizes what perfect graphs are. And this was actually proved in 2006 by Chudnovsky, Robertson, Seymour, Thomas. And the paper which proves this is very long. It's 178 pages. So the proof is very complicated. Anyway, so that concludes the, lecture about the graph colorings. And yeah, from next time we will start a new topic on planograph. So I will see you in next video. Thank you for listening.